Welcome back to this session of discussion on applications of Laplace equation. In our previous videos, we have discussed two applications of the Laplace equation. One, the parallel plate capacitor, and another one, the coaxial cable. Now, I would like to explain the application of Laplace equation to a spherical capacitor. Are two concentric cylinders carrying charge separated by a dielectric medium. So this problem explains you how to apply Laplace equation to a spherical coordinate system. So I have taken two problem statements here. According to the first one, we have to find the capacitance between two concentric spheres of radii r equal to b, r equal to a. So b is greater than a. That means b is the radius of the outer sphere and a the inner sphere. And the potentials are also mentioned. V equal to 0 at r equal to b. R equal to b means outer sphere. Potential is 0. That means it is grounded. So the potential on the inner one, it's not specified here. You can take any value on the inner sphere. We shall assume accordingly. In the second statement, we have to derive the expression for capacitance for a concentric spherical capacitor. That means two charged spherical conductors separated by a dielectric form a spherical capacitor. And you have to write or derive an expression for capacitance using Laplace equation. Make suitable assumptions. Now here I have two concentric spheres. The inner one, let us say, is of radius A, the outer one of radius B. Let the outer be grounded, that is mentioned at potential 0. Then we shall assume that potential value on the inner sphere as V naught. With these two boundary conditions, that is V equal to V naught when R equal to A and V equal to 0 when R equal to B. With these two boundary conditions, we can find potential distribution between the two spheres using Laplace equation. So first, consider the Laplace equation. Consider the Laplace equation. That is, we know that Laplace equation is given by del square V equal to 0. The Laplacian of potential V can be expanded in spherical coordinate system. That is, it is given by 1 by r square dou by dou r into r square dou v by dou r. This is the first term of the expansion. Second one is 1 by r square sine theta dou by dou theta of sine theta into dou v by dou theta. This is theta. Theta. Plus the third term is with respect to the third variable, that is phi. So 1 by r square sine square theta dou square v by dou phi square. Since Laplacian is a scalar, there are no unit vectors. You can observe it. But from the discussions of the boundary conditions, we can say that potential V is a function of radius r only. The potential doesn't change with respect to theta. So dou v by dou theta becomes 0. Dou v by dou phi also becomes 0. So the last two terms do not exist. Therefore, we can have the equation 1 by r square d by dr r square into dy by dr is equal to 0. This equation is left now. So from this equation, we can find V. See here, V is here. We can take out this V from this equation to get an expression for potential distribution. So we shall start with 1 by r square. Let us send all terms to the right side one by one. So 1 by r square, after putting it to the right side, becomes 0. R square into 0 is 0. So dou by dou r into r square dv by dr is again 0. To remove the differentiation from left hand side, we shall integrate on both sides. So after integration, left hand side, we have r square into dv by dr. The right side, integration of 0 is 0 plus the constant of integration c1. C1 is any arbitrary constant. Now, further, r square can be taken to the right side because we want only v here. So it becomes c1 by r square. So one more integration needed now. We shall integrate now. So v is equal to c1. Integration of 1 by r square is minus 1 by r. Okay, so if integration of 1 by r square, if you want to have, so r square is can be taken as r power minus 2. So now the integration of this one is r power minus 2 plus 1 divided by minus 2 plus 1. So this is going to be r power minus 1 divided by minus 1. The minus 1 is minus, r power minus 1 is 1 by r. So we can directly write that it is minus 1 by r plus the constant of integration. We have integrated twice. So two constants of integration, and this is our equation 1. So the potential distribution in a concentric spherical system is given by the equation 1. So from this, we can say that potential V inversely vary with respect to R, where C1 and C2 are arbitrary constants depending upon the boundary conditions. So therefore, C1 and C2 can be found from the boundary conditions. Boundary conditions. Usually boundary conditions will be specified in the problem itself. If not, they can be appropriately assumed. Now let us go with first boundary condition. We know that outer sphere is grounded, therefore V is equal to 0 on the outer sphere, but the radius of the outer sphere is B. So the first boundary condition, V equal to 0 at R equal to B. Therefore, equation 1 becomes, after applying the boundary condition, V in place of V 0, C1 is a constant, minus 1 by R is the radius. Here in this case it is B plus C2. So from this, C2 is equal to C1 by B. B is a constant given in the problem itself. C is still not known. We shall come back to C2 after finding C1. Now the second boundary condition, that is potential V is equal to V naught at the inner sphere of radius A. Therefore, equation 1 now becomes so in the equation 1, left side is V. Now V becomes V naught. First term C1 into minus 1 by R becomes minus 1 by A plus C2. C2 is already having some expression minus C1A. So C2 is available here. So in place of C2, I would like to write C1 by B. Now the C1 becomes common factor. So we can write this as 1 by B minus 1 by A. V naught. The constant C1 is now is equal to V naught by 1 by B minus 1 by A. This is the value of C1 because V naught and the radii A and B are known. Now we shall get back to C2 once again to complete its calculation. Now C2 is equal to C1 by B. Therefore C1 is V naught divided by 1 by B minus 1 by A into 1 by B. This B in the denominator is 0. This is about C2. Now C2 and C1 are ready. Then we can complete our equation of potential distribution. Therefore, the potential distribution now becomes V equal to, so in the equation what is there, C1 to minus 1 by R plus C2 now becomes, in place of C1 we shall write V naught by 1 by B minus 1 by A. This is our C1. Minus 1 by R is there in the V itself. In place of C2, we have V naught divided by 1 by B minus 1 by A into 1 by B. So we know what we have. This term is coming from C1. And this is from C2. Finally, V becomes, so you can simplify this one by taking the common factor V naught divided by 1 by B minus 1 by A. Take it out as a common factor. So we are left with 1 by R plus 1 by B. So this can also be written as 1 by B minus 1 by A into 1 by B minus 1 by R. So everything is constant except R here. We know that B is the larger radius than A. That's why 1 by B is smaller than 1 by A. That means the denominator term is negative. Similarly, if you observe this term also, 1 by B is the largest radius in the system. So R is always less than B. So that's why this is also negative number. So finally, we can have a proper expression for potential distribution. That is V is equal to V naught divided by 1 by A minus 1 by E is a better one. It becomes a positive number now. Similarly, 1 by R minus 1 by B becomes another positive number. So this is the potential distribution in volts. Let me call this equation 2. Now it's time to find electric field distribution, that is E. E is given by negative gradient of potential. For spherical coordinate system, negative gradient of potential is given by dou V by 2R R minus 1 by R dou V by dou theta A cap theta, that is theta component, 1 by R sine theta dou V by dou phi. So, you know my next step. Potential doesn't vary with theta and phi. Those two terms are not needed. We need only potential differentiation with respect to R. Now, we shall differentiate V now minus d by dr of V. The equation for V, we copy from equation 2. So it is V naught divided by 1 by A minus 1 by B into 1 by R minus 1 by B into A cap R. So we got this step from equation 2. Equation 2. Now it's time to differentiate with respect to R. First, identify the constant terms. They are V naught divided by 1 by A minus 1 by B. A, B, V naught are all constant. Differentiation of 1 by R. You know, the differentiation of 1 by R with respect to R itself is given by differentiation of R power minus 1. So differentiation of R power minus 1 is minus 1 into R power minus 1, that is minus R power minus 2. It is minus 1 by R square. So 1 by R after differentiation becomes minus 1 by R square. Differentiation of 1 by B with respect to R is 0. We are left with A cap, R the unit vector. So here minus into minus plus. Finally, the electric field is given by V naught divided by 1 by A minus 1 by B into R square in the denominator, A cap R. This is the field distribution in a spherical capacitor. What you can call this equation 3, and it is in volts per meter. 2 points can be observed here. The first point is E is inversely proportional to R square. Electric field is inversely proportional to R square in the case of a point charge. So as the distance increases, a spherical conductor having charge behaves like a point charge. Right, and the direction of electric field is radial, A cap R. So in a parallel plate capacitor, in a spherical capacitor having two spheres here, the electric field between the two spheres is in radial direction. This is radial direction. So radial direction is existing in all the directions of the sphere, and all are perpendicular to spherical surface. So this proves our concept what we discussed in the boundary conditions. And this is our electric field. Electric field is zero inside the inner sphere. This is already proved in the first module. For a sphere having charges on the surface, the electric flux density D inside the sphere is always zero, so E is also zero, right? And the inner cylinder is positively charged, inner sphere, and outer sphere is negatively charged. So because of this, electric field is also zero outside the outer sphere. So the electric field and also the potential field V exists between the two cylinders. After this, as usual, we find electric flux density D in coulomb per meter square. So D is equal to epsilon naught E. So D is equal to epsilon naught V naught 1 by A minus 1 by B into R square A cap R coulomb per meter square. This multiplication of epsilon naught with E. But to find the charge density, that is surface charge density on the inner sphere. Inner sphere has charge on its surface, so surface charge density can be found. And as per the boundary conditions between, conducting medium and dielectric medium, that means if you have conducting and dielectric medium side by side separated by a boundary, we have the relations, that is D and E both are perpendicular to the conducting surface. The conducting surface is having charge, and rho S is given by the magnitude of D. D is normal. The normal component of D gives rho S. Therefore, modulus of epsilon naught V naught 1 by A minus 1 by B into R square A cap R falls within the modulus sign. But as we did in the last derivation also, the surface charge exists only on the inner sphere. The radius of the inner sphere is A, outer sphere is B. Between A and B, surface charge is zero. Surface charge exists only on the inner sphere of radius A. Therefore, here R equal to A. Now, rho S becomes epsilon naught V naught 1 by A minus 1 by B into A square. Rho S is a scalar. The modulus of unit vector is 1 coulomb per meter square. This is the surface charge density of the inner sphere. Next, we shall find the total charge stored on the inner sphere. So which is given by surface integral of rho s, and we know that rho s is constant. So integration of ds gives total surface area of the inner sphere. Because we are finding total charge on the inner sphere, that's why surface area of the inner sphere required. So finally, Q is equal to rho s. So we shall copy the rho s from the previous step. Epsilon naught V naught 1 by A minus 1 by B into A square. This is rho s into surface area of the inner sphere. Area of a sphere is 4 pi r square. In this case, it is 4 pi A square because total charge is only on the inner sphere. And we know that A square is cancelled. Finally, Q becomes 4 pi epsilon naught V naught divided by 1 by A minus 1 by B. In coulombs. The last part of the discussion is finding the capacitance. Capacitance C. C is given by charge on the inner sphere, total charge on the inner sphere divided by potential difference. This is the total charge, which is calculated in the previous step. Potential difference between the two spheres is V naught minus 0. Therefore, C is equal to total charge is 4 pi epsilon naught V naught divided by 1 by A minus 1 by B into the potential difference is V naught. So V naught cancelled. So finally, the capacitance is equal to 4 pi epsilon naught divided by 1 by A minus 1 by B. This expression gives capacitance between the two concentric spheres in farads. This completes the derivation of this application. Thank you.